A couple of weeks ago, scientists with NASA and the University of Montreal announced the discovery of this planet. They also released a paper that describes some of the surface dynamics going on it and its atmosphere. I've got a short video that I put together that talks about the discovery, and then I'd like to go a little bit more in depth talking a little bit about the research that they published. So stick with me and let's get into this. I'm Cameron and this is my channel. Welcome to the Sexy Universe. Whenever a planet passes in front of a star, there's a little flicker of light because the planet blocks it every time. Not all of it, of course, but just enough that you would see a flicker in the flame. This is the Spitzer Space Telescope, which has been up in orbit since 2003. It's being used as part of a broader mission called TESS, T-E-S-S, which is a mission to find exoplanets. An exoplanet is a planet that orbits a star other than ours. Researchers just found and characterized another planet, and I'd like to talk about it. The planet is going around a type M star, which is the smallest we can see. It's a red dwarf, and for reference, our sun is a type G star. And once again, for reference, if our sun is the size of a basketball, then the star it's going around is about the size of the top of this light bulb. 1/5 the size. The name of the star is LP 781-18, and it's in the constellation Crater. And it's between the brightest star up in the corner there, the brightest star in the Hydra, and that over there is the brightest star in Virgo. So it's not far off the plane of the ecliptic, the line where the sun goes through. Beginning on the star map, there's the bright star in Virgo. And if we zoom in on our target, we have to go in about 82 light years to find our star. Here's a drawing of that planetary system. The red dwarf is in the center. The first planet discovered was labeled B. The second one discovered was labeled C. And the third one, which was just discovered, is labeled D. Planet C is about 2.5 times the size of the others, while these other two planets are about the size of Earth. And they're all relatively close to their star compared to the Earth. Planet B goes around it every 22.5 hours, Planet D goes around every 66 hours, and Planet C goes around about every 120 hours. So that bigger planet, that's 2.5 times the size, it's actually 7 times the weight of the newly discovered one. And the newly discovered one is kind of stuck, so it always shows the same side to its star, just like Earth's moon does with the Earth. And the bigger planet pulls on it every time it goes past. This is Jupiter's moon Io, and Jupiter pulls on it, which heats up its core, so it's covered with volcanoes. And it turns out that's what's going on with this new planet that we just discovered. As promised, we're about to go a little more in depth. If you're enjoying this video so far, now is a good time to hit the like button and leave any thoughts you have in the comments section because it helps the YouTube algorithm. The first thing I'd like to break down is this image from the research paper. The graphics show the image data that was collected by TESS and the Spitzer Space Telescope. And beginning with this image on the right, you can see the star in the middle, and then each of the planets is denoted by a different color. The graphic at the top is a scatter plot of light data from TESS, and the graphic beneath it is the same data from Spitzer. And you'll notice colored tick marks that show up throughout the graph. The yellow are when the smallest planet, the innermost planet, passes in front of the star, and then the magenta ones are when the second planet does, and then the blue tick marks show when the outermost planet, which is the largest, passes in front of the star. And in this image, we can see the percentage drop in light flux, the percentage drop in light that's perceived by these telescopes when each planet passes by. And you can see the largest drop is from the one that's the farthest out, and then the middle and the one on the inside respectively. To explain the next part, I'm going to start with a quick review of the interior of the Earth. The innermost core is solid, and then you have a more liquid core outside of that. It's that liquid core that generates the magnetic field around the Earth. And then outside of that liquid core, you have a mantle that's kind of stiff but still flows. And the researchers assumed that this planet has the same inner structure as the Earth. It's about the same size, so there's no reason it couldn't. And because the mantle is made up of a stiff liquid, rocks that are mostly melted, they create these convection currents that go from the heat source, which is at the inner core, then go up to the surface of the planet. And ultimately, the energy that powers all this actually comes from decay of radioactive isotopes within the Earth. And when those atoms break apart, they release energy, which then becomes heat. And that heat is ultimately released when the mantle is forced up to the crust of the planet. The second source of heat that's powering the geological dynamics of this planet is tidal forces. The tidal force happens when another body outside of that planet pulls on it. So the Earth receives some tidal force from the moon. And that pull from the moon actually does heat up the interior of the Earth to some degree. And it does it by pulling on the mantle. And when it pulls on the mantle, it creates friction between the different molecules within that mantle. In the case of this newly discovered exoplanet, the larger planet that orbits outside of it is a source of tidal pull. So every time that larger planet passes by, it pulls on the mantle, it pulls on the interior of this planet, and creates some heat. This equation shows the energy that's produced from that tidal force as a function of the interior temperature of that planet. So in green, I've marked where it defines that function, the energy as a function of temperature. Underneath that, I have a term that I've highlighted in blue that defines the surface area of the planet, 4 pi r squared. So this equation actually shows the energy flux from the surface of the planet per square unit. In this case, they calculated it by square meters. And you may remember that a meter is just 3 feet and 3 inches. So just over 1 square yard. In red, I've marked the term 0.53. That's just a constant they used to work out their units. The term in yellow shows how much energy it takes to start pulling on those rocks in the mantle. And the term in magenta shows how much energy you get out when you create that friction. So the overall energy released is a function of the amount of energy that you get out of it divided by the amount of energy you put into it. This graph shows the different energy regimes for the mantle of that planet. The middle line I've just highlighted in yellow. To the left, it's a solid mantle, and to the right, it's a partially liquid mantle. There's a green line, which I've just highlighted in green, and that shows the status of the Earth's mantle. There's a blue line, which I've just highlighted in blue, and that's the state of Io, Jupiter's moon. In magenta, I've just highlighted the line of convective force. And you'll notice that when it reaches the part where it's a partially liquid mantle, it breaks into 4 possible regimes. And the tidal force line, which I've just marked in orange, also breaks into 4 possible regimes at the partially liquid mantle point. And you'll notice these 4 dots which I've circled. These are the points where you reach equilibrium between those convective forces and those tidal forces. And in this case, all the possible equilibria based on these models show that it must be a partially liquid mantle. Furthermore, the state of that mantle exists between the line that describes the Earth's mantle and the line that describes Io's mantle. So this planet is going to have much more volcanic activity than Earth, but less than Io. Finally, I want to talk about how the authors of this study describe the climate state of this planet. Spectroscopic analysis shows that the planet's atmosphere is mostly composed of hydrogen, oxygen, and carbon. So that's going to add up to mainly water, H2O, and carbon dioxide, CO2. Well, carbon dioxide and water are both greenhouse gases. So it's possible that this planet actually is subject to a runaway greenhouse effect, much like the planet Venus. In which case you'd have a very steamy atmosphere with lots and lots of heavy clouds. If it's in this state, then as water goes to the top of the atmosphere, radiation from the star would break apart the hydrogen and oxygen, and then those atoms would be able to escape into space. So the atmosphere would be slowly blowing away. However, we know that one side of this planet always faces toward its star, and that means the other side is always dark. And on the dark side of the planet, it's possible that it gets cold enough that water and CO2 can both form ice crystals, in which case you would have caps of ice most likely near the poles on the dark side of the planet. And that would mean you would have areas where the climate would be very Earth-like, especially in the area around the transition zone between the lighted side of the planet and the dark side of it. They even speculate that you could have pools and streams of water, which would raise the possibility that life could evolve there, which makes this all the more interesting in my opinion. Thanks for watching this video. If you enjoyed this content, please hit the like and subscribe buttons. And leave your thoughts in the comments section because it helps the YouTube algorithm. You can also follow me on Instagram and TikTok. I'll put the links in the description. I'll also link to this paper in the description. And I'll see you next time on The Sexy Universe.